Right now, a silent, multi-billion-dollar calculation is happening inside the world's largest data centers, and it has nothing to do with intelligence. It is a matter of basic arithmetic. If a company spends $100 million training an artificial intelligence model, that is a one-time fee. But the moment millions of people start using that model, every single generated word costs a fraction of a cent. At scale, that math becomes catastrophic. For the last few years, the tech industry operated under a simple assumption: buy as many general-purpose graphics processing units as possible, and the software will figure out the rest. But in 2026, that assumption has run into a physical and economic wall. The industry is waking up to a reality where running these models is far too expensive to sustain. The era of brute force compute is over, and a new, quiet war over custom silicon has begun. To understand how we got here, we have to look back to a concept called the hardware lottery. Coined by computer scientist Sarah Hooker in 2020, the theory points out a bitter truth about computer science. Software architectures do not win because they are mathematically the most elegant. They win because they happen to run efficiently on whatever hardware is cheapest and most available at the time. In the early days of deep learning, the hardware that happened to exist was the graphics card, built not for artificial intelligence, but for rendering three-dimensional video games. Because gaming required calculating millions of pixels simultaneously, these chips were excellent at parallel matrix multiplication. The dominant AI software design of our era, the Transformer, succeeded largely because it fit the architecture of these gaming-derived processors perfectly. It was a historic stroke of luck for NVIDIA, but it created a dangerous path dependency. We built an entire software revolution on top of chips designed to render video games. The fundamental bottleneck of modern computing is not how fast a chip can calculate. It is how fast it can move data from its memory to its processors. This is known as the memory wall, and it is governed by a brutal physical reality. Think of a computer chip as a master chef and memory as a pantry. In a standard graphics card, the pantry is high bandwidth memory, or HBM. It holds a massive amount of ingredients, but it is located down the street. Every time the chef needs to make a calculation, they must wait for a delivery truck to bring the data over. If you are training a model, this is fine because you process data in massive batches. The truck is always full. But when you are running a model for a single user, a process called inference, the chef only needs a single grain of sand at a time. The delivery truck still has to drive down the street, burning time and energy for almost nothing. Your expensive processor spends most of its life sitting completely idle, waiting for memory to arrive. To bypass this physical bottleneck, the largest technology companies in the world are rigging the hardware lottery. They are no longer waiting for off-the-shelf chips. Instead, they are designing their own custom silicon, specifically tailored for inference. These chips are called Application-Specific Integrated Circuits, or ASICs. Unlike a general-purpose graphics card, which contains legacy hardware for rendering graphics and managing complex queues, these custom chips are stripped down to the bare essentials. Google has its tensor processing units, Meta has its training and inference accelerators, and Amazon has its inferential line. By designing their own silicon, these hyperscalers can make different physical trade-offs. They can place a massive amount of incredibly fast memory, called static random access memory, directly on the silicon die next to the execution units. The pantry is no longer down the street. It is right next to the cutting board. The motivation behind this shift is pure survival economics. During the training era, buying graphics cards from a single dominant supplier was an acceptable cost of entry. But as the industry shifts to deployment, the unit of currency is no longer the floating point operation. It is the cost per token, the individual pieces of words generated by the model. If you rely entirely on general-purpose chips, you are paying a massive premium. You are paying for hardware features your software does not use, and you are paying the high profit margins of the semiconductor designer. For a company serving billions of users daily, even a tiny reduction in the cost of generating a single token translates to hundreds of millions of dollars in annual savings. By deploying custom inference silicon, tech giants can run models at a fraction of the cost. This economic divide is creating a two-tiered system: those who own their silicon and those who must rent it at a markup. The rise of custom silicon is now forcing a massive evolution in software design. For years, Researchers focused on making models larger, assuming the hardware would scale to meet them. Today, the reverse is happening. Software developers are redesigning model architectures specifically to fit the physical constraints of these new custom chips. We are seeing the rapid adoption of architectures like Mixture of Experts, where only a small fraction of the model is activated for any given query. We are seeing state space models and speculative decoding techniques gain traction. These approaches are not necessarily chosen because they are fundamentally smarter or more capable. They are rising to prominence because they minimize memory traffic. They are designed to play nice with the specific SRAM and high-bandwidth memory layouts of the new silicon. The hardware lottery is being played in reverse. The physical limits of the silicon chips are now deciding which mathematical algorithms survive. But designing custom silicon is only half the battle. You still have to build it. And this is where the tech giants run into a shared, physical bottleneck: advanced packaging. Even if you design the most efficient custom inference chip in the world, actually manufacturing it requires access to highly specialized fabrication plants and advanced packaging technologies, such as chip-on-wafer-on-substrate. Currently, a massive portion of the world's advanced packaging capacity is controlled by a single company in Taiwan. This creates a high-stakes game of logistics. Tech giants are not just competing over who has the best chip designers. They are locked in a silent war to secure wafer allocations and packaging capacity years in advance. A brilliant custom silicon roadmap is useless if your designs are stuck in a queue waiting to be printed onto silicon. We are entering a highly fragmented era of computing. The illusion that a single, universal graphics chip can power the entire future of artificial intelligence is fading. Instead, the landscape is splitting into a complex ecosystem of highly specialized hardware. This shift marks the true vindication of the hardware lottery. The software architectures that will define the next decade of technology will not be discovered in a vacuum of pure mathematics. They will be shaped, constrained, and ultimately selected by the physical properties of the custom silicon humming inside data centers today. In this new era, the ultimate advantage does not belong to those who build the largest models, but to those who control the physical pathways of the silicon itself. The lottery is still running, but the players have finally realized that to win, they have to build the machine.